So the presentation this evening is probably going to fall into two parts. Firstly, about how geotechnical engineers and structural engineers can work together. And then secondly, how we can apply that in soil structure interaction. So the first bit of it may be familiar to some of you because it has been presented previously in other forums, but still valuable to repeat. So, cool. It's all right, we'll get there. There we go.
Yeah, good to go.
Okay, the form of the primary structure and the foundation system were jointly selected by the structural and geotechnical engineers in consultation with the architect and the client. I think that would have been quite foreign language 20 years ago, where what we would see is a geotechnical engineer producing a report, handing it to a structural engineer says thank you and goes off and designs foundations and structure and the whole box. But I'd like to think that now it's quite different. We're seeing a lot more collaboration happening between us all here in geotechnical and structural, and certainly like to see us doing more of that. And maybe we could talk more about this at the end of the presentation. Just where are we at the moment in relation to that?
And definitely keen for your thoughts on that. I think we would freely admit that we're certainly not there yet, and we've got a lot of work to do in this space still, but you know, that's perhaps an aspirational statement, and keen for your thoughts on where we are along a continuum of making that statement a reality. Look, and I suppose we're not starting from the start. There is a lot of really good work happening in the collaboration space between structural engineers and geotechnical engineers, and here's a couple of examples we've put up on this slide. There's some really good work has been done by the Ministry of Education in the Designing Schools in New Zealand requirements. That document's gone through several iterations, but was sort of formally launched as a set of requirements if you're designing school buildings last year, and that's a really good document to be a sort of a founding document for this conversation, I guess. And if you haven't referenced it or seen that document, we really encourage people to do so. And the other area of collaboration that's ongoing at the moment is in the low damage seismic design space. It's a dual project being undertaken, funded by MB and run through Engineering New Zealand with input from geotechnical engineers, structural engineers, architects and other building consultants around developing a set of guidelines for low damage seismic design, and that is another collaboration between structural and geotechnical engineers. It hasn't been formally published yet, but hopefully will be later this year or early next, and certainly would encourage you to keep an eye out for that.
Certainly, from my involvement with the low damage seismic design work, the repeat theme that we keep hearing is the need to look at a building holistically, both, you know, thinking about architectural, thinking about structural, thinking about geotechnical, building services and other disciplines all need to be working together towards the same objective with what we're trying to achieve in low damage seismic design. So it's a lot more than just collaboration between geotechnical and structural, there's the other disciplines as well.
And I suppose in the past, that topic's often been seen as a structural engineering issue, but we're certainly trying to get a clear message across that it's not just about structural engineering, it's about whole buildings. And just thinking about some really basic examples of where structural and geotechnical engineering collaboration is really important, and a couple of examples, and these slides are borrowed from Alistair Catnack at Dunning, so thanks Alistair for your great sketches. You know, the top example there, a portal frame warehouse, and the top left being a fixed base portal where we're trying to generate decent moments at the base of that portal frame. But in order to do that, we need a soil and a foundation solution that will support that torsion or that moment that we're trying to generate at the base of those portal frames. And so, you know, we need to be collaborating between our structural and geotechnical consultants to make sure that we can generate that amount of moment in those portal frame bases, as opposed to the one on the right, where perhaps the soils aren't so great, and so we've gone to a pin-based portal solution, and that's thrown a bit more demand up into the structure, so the structure's got a bit heavier, but the demands on the foundation aren't as great as they would be for the solution on the left. And so a real simple but tangible example of structure informing geotech, geotech informing structure, and the need to collaborate to make sure we don't get a perverse outcome where we're fighting one thing off against the other. The example at the bottom there, again, a reasonably modest multi-story building, and, you know, looking at options between a shear wall building or a distributed frame type structure. So the shear wall building might have far greater push pulls at the ends of those shear walls, and we obviously need to be able to generate that capacity out of the foundation system. So again, collaboration with a geotechnical engineer to make sure we can readily achieve those sorts of push-pull demands, and that makes sense in terms of what the structural engineer is trying to achieve. The example on the right with the frame, more distributed foundation demands, lower push-pulls at the end, and might suit a site that has poorer founding conditions than the need for big push-pulls in the shear wall option.
Probably just taking that with a couple of examples, like the bottom left there, probably not a solution you'd want to try in the Hutt Valley. Try and resist those big uplift resistances in the ground conditions in the Hutt Valley is going to be incredibly difficult. Whereas here in Wellington, if you're on a rock site, for example, then yes, you can do that. So in the Hutt Valley, you might want to look more at the image on the right. New Zealand Geotechnical Society Module 4 is a great document providing us with some really good guidance on selection of foundation types for various ground conditions. But what we'd like to talk about here is selection of foundation types and thinking about the structure in conjunction with the foundations. So first of all, think about shallow foundations, a really good economic solution for the right ground conditions, but one that may be limiting to you in the terms of what structure you can actually put on top. So you need to be thinking about selecting that foundation type and the form of the structure at the same time, because those shallow foundations will have limited uplift capacity and they'll be probably more flexible than a pile foundation. Thinking about the deep foundation solutions, probably the main point I want to make here is all piles are not equal, and probably describing that by an example would be over the last couple of decades in Wellington here, we've been building a lot of medium-rise buildings. They've typically had frame structure or shear walls. With Wellington's high seismicity, we're trying to deal with huge uplift loads and compression loads on our foundations. And the economic solution we've come up for that has been large diameter board belled piles. And these bells are big, like 3 meters plus in diameter. Post Kaikoura earthquake, there's been a lot more concern about damage to buildings and the need for low damage seismic design. So we're starting to see a lot more base isolation with nice stiff structures sitting on top of that base isolation. But the challenge for the geotechnical engineer we have there is those stiff structures have got a much lower tolerance to differential movement. So those board belled piles, you know, they might take heading up towards 100 millimeters of movement to actually develop their full capacity, just not the right solution. So we need to completely rethink the foundation systems, and what we're doing typically around the city at the moment with base isolated buildings is using driven piles. Ground improvement offers a great opportunity to actually allow a number of different foundation systems and structural systems to be considered, which wouldn't otherwise be possible on the site. So think about ideas like rocking foundations and the like. So it can be a good solution to actually introduce a whole new way of dealing with your structure.
And just wanted to briefly touch on problems and solutions around hillsides. That's obviously a very real topic in places like Wellington, but also lots of parts of the country. And so, you know, various different solutions, benched or benched and tied back. Need to think about where base shear takeout is happening in various different structures, whether it all happens at the bottom or whether it's distributed up the site, whether you want to use tiebacks in order to support your building structures, and that will also be influenced on the type of structures that you might look to build on top of those. And so obviously really key to have good collaboration and dialogue between the structural and the geotech engineer when you're dealing with hillside sites and those sorts of problems. You know, there are various variants that we haven't considered here. You might think about options to just have a big deep cut and a retaining wall tied back into the hillside independent of the structure. You might be trying to avoid much excavation and retaining on the structure on the hillside at all, and build a structure that's sort of poled and sitting very lightly on the ground. So all of those sorts of things are things that need early conversation and collaboration between geotech and structural engineer.
Probably examples which could describe that would be traditionally domestic housing development in Nelson compared to Wellington. In Nelson, you've got some serious slope stability problems on relatively gentle slopes. So a common solution for a house is actually cutting into that slope. It has the benefit of actually forming a nice flat building platform to work on, and also gives you the opportunity to actually put in some subsoil drainage and actually improve the stability of the slope. In contrast, here in Wellington, we have much steeper slopes and probably not really the same stability problems. All we've got is that mantle of weathered rock or colluvium at the top, which might slip off. So rather than stepping into the slope, we tend to sit on top of the slope with buildings that just sort of step down the slope. So just thinking about the geotechnical conditions and what the solutions might be on top of that. So far, we've been talking a lot about the conceptual stage of a design, all about selecting the right foundation and structural system. Now I'd like to talk a little bit by this example around how, as geotechnical and structural engineers, we can work together during the develop design stage. So thinking about how we go about designing a raft foundation. What would typically happen is the geotechnical engineer comes up with some spring stiffnesses to provide to the structural engineer to do the first run of analysis on the raft foundation. Output from that analysis is the actions in the raft, as well as the distribution of the bearing pressure on the subgrade. But that distribution of bearing pressure actually also influences the amount of settlement you get and the distribution of that settlement. So the geotechnical engineer takes that distribution of settlement and distribution of bearing pressure and calculates settlements, divides pressure by settlement to give a new set of spring stiffnesses, and feeds that back to the structural engineer, who then repeats the structural analysis. So this feedback loop continues until the geotechnical models and the structural models are agreeing. So a good example of how we can work collaboratively together to actually come up with the answers.
And also bring into mind this idea of iteration. You know, it's not or you go do your work in isolation and you tell me the answers and then I'll be able to finish my design. There is within this an ongoing need for collaboration, iteration, dialogue to get to a solution that is achieving everyone's outcomes.
That's what I like about the example before. Because of the design process, it actually forces us to talk. But the challenge I'd like to put to all of us is, rather than being forced to talk, let's just talk. So each time a geotechnical engineer provides a structural engineer with parameters, what we need to be doing is the structural engineer needs to feed back to the geotechnical engineer comments on those parameters and what the conclusions we're drawing from them. Like an example might be the spring stiffness that we've given for a pad foundation is quite soft, and that's putting some quite big actions in the structure because of differential movements. well, tell the geotechnical engineer about it. It gives the opportunity to think, oh, maybe I was being a bit conservative there. Maybe we can tweak that parameter. Or why don't we undercut a bit and just make that parameter a bit stiffer by putting in some hard fill? You know, if we don't have those conversations, we're not going to develop those designs. And perhaps equally importantly, we're not going to actually get to understand each other's discipline. So if we have those conversations, we'll actually learn more about each other's discipline and then be able to provide each other with a much better service. Communication. The image up in the top left-hand corner is how a structural engineer may see a building, a fixed base. The image in the bottom left-hand corner is how the geotechnical engineer sees the same problem. A summary of a soil profile in a table or a simple cross-section. The challenge is, why don't we actually bring that together in one picture and think about the foundations and how they're actually interacting with the soil and the structure above. The image that's actually there on the right-hand side is probably not a good one. What we should have done is drawn the rest of the structure above and shown those shear walls or those braces or whatever. So then when we have conversations, we can talk about why the piles have different stiffnesses, why the structure has that limited tolerance to differential movement. So we actually can keep that communication going rather than these very siloed ways of communicating, which we used to do.
Yeah, and I know, you know, I'm certainly guilty of drawing the top left-hand image on numerous occasions, and I'm sure Stuart's produced a fair few of the bottom right, of the bottom right. And the challenge we're suggesting is we need to collectively get away from that and start talking in more of a common language. And a good example of the collaboration and how this can really work is with a project that Stuart and I were working on a few years ago with the new control tower out at Wellington Airport, where the design started with a fixed-based structure that had really high seismic loads. It's on a soft D soil site. It's an importance level 4 structure. It's a 7-story high tower, and so the foundation demands were just enormous. And we were coming up with really high overturning demands on a site that has got fairly poor soils. And so in order to deal with that, we're needing to dig out the top 3 or 4 meters of very soft sediments and found a raft foundation down on some better layers 3.5 or 4 meters down. Even then, and with a absolutely massive raft foundation, we still couldn't stop the thing from wanting to tip or rock, and so we're having to add supplemental soil anchors in order to resist the tensions on the leading edge of that raft foundation. And it just kind of wasn't working, to be perfectly honest. And the solution was driving, or the conditions were driving a solution that just didn't make a whole lot of sense. And it wasn't until we kind of got around the table together and started talking a bit more around, you know, what some of the opportunities might be for the structure and how that kind of worked with what the ground conditions were, that we realized, well, we need to excavate out the top 3.5 to 4 meters of ground anyway. So why don't we use that depth to create a lower raft foundation and a layer to allow base isolators to be installed, and then an upper raft foundation. And by doing so, we drop the seismic demands on the foundation system hugely by a factor of 3 or 4, and we can make a far smaller foundation system work, and the net result being something that was cost neutral, if not provided a little bit of a saving on the original solution, because the ground conditions facilitated installing a layer of base isolation and lead rubber bearings just due to the site constraints.
So a 3-way win. We ended up with a low damage seismic design, we ended up with less structure, and we ended up with less foundation. So,
And then it also enabled the architect to kind of do some other things up top, and they decided to put the structure on a lean, and perhaps that's a talk for another day, but a good outcome in general terms. Wanted to also touch a little bit on design phases and what we might be expecting from each other at certain design phases, because at times I think we sort of don't talk about this sort of stuff enough and aren't clear enough with each other about what we expect from each other at certain stages in the design. So, you know, the concept design phase is all about information gathering, site investigations and factual reporting for the geotechnical consultants. It's about, you know, getting around the table, talking about options and ideas and opportunities, and also talking about challenges and risks and things that we want to drill into in more detail at subsequent design phases. Moving into preliminary design, it's about testing options and refining, you know, which options are viable and which options might be preferred. And then as structural engineers, we're getting into preliminary sizing. So we're starting to design structural members, design foundation systems and options, and start putting sizes to foundation solutions, piles or pad foundations or the like. And then at the end of preliminary design, we'd probably, as structural engineers, expect a report from the geotechnical consultants, you know, summarising all of that, and that's often a really good deliverable or kind of deadline in the project that sets the rest of the developed and detailed design phases up to really, you know, start developing and finalising the design based on some very concise and well thought through, you know, geotechnical engineering inputs. Anything to add there, Stuart, from a geotech perspective?
Only really to reiterate, the product is not a report. The product is a design, yeah, we just hear too much of it that the request is for a report. That's just some little formality that happens later on. It's all about working together, getting the right design, and then yes, documenting it at the end.
And then, you know, from that prelim design milestone, we're into option refinement and detailing. So we want to have a really good understanding of what it is we're doing by that stage, so that we can just, you know, finish off our designs through to the end of detailed design and then into construction and implementation. And I suppose, you know, again, that implementation phase in construction is another opportunity to collaborate and make sure we're talking to each other about that implementation, getting the geotechnical engineer on site to help confirm or verify the conditions they were expecting to find as part of their investigations, and perhaps too often, you know, we call a geotechnical engineer up at the end of the project and they hadn't even known you'd kind of got underway.
Yeah, I'd certainly like to reiterate that, you know, projects in the past, I've seen problems just because the geotechnical and structural engineer haven't agreed right at the beginning who's doing what, or worse still, the geotechnical engineer hears nothing until, oh, there's a bit of a problem here, don't want to take the risk for that, quickly call up the geotechnical engineer, which is not the way to do it. We've got to be involved together right the way through.
Sort of moving into the soil structure interaction part of the talk, and thought we'd put this slide up just as a starter for that conversation, not to shine any particular light on Centreport or the reclaimed land there, but just to reference the fact that our urban centres and built environment in New Zealand is located in some fairly challenging environments, and not just here in Wellington, but throughout the country. And this geotechnical and structural interaction has really been shown over the past 10 or so years since the Canterbury earthquakes to be really quite important, and when not done well can lead to some adverse impacts. You know, there was some damage at Centreport during the Kaikoura earthquake, and a lot of that was to do with port infrastructure, the likes of the Thorndon container wharf out over this edge here, which was a fairly stiff, rigid structure right against a and rigid and brittle structure right against an area of reclaimed land that was prone to significant ground movement in an earthquake. So, you know, that certainly wasn't a good example of good soil structure interaction and collaboration, albeit a piece of infrastructure that was built many years ago. And there was also obviously some buildings that suffered significant damage. So Stats building in here, which has since been demolished, and the BNZ building in here, which have been demolished. And so perhaps an outcome out of that was perhaps a little bit more thought around the types of structures we're building on certain sites and site profiles may have potentially led to better outcomes. And so a building in here, the Custom House building, which is a stiffer shear wall building, is still standing, but the buildings that were flexible frame structures, this one here and here, or in particular the modern buildings here and here that have since been demolished that were flexible frame buildings, you know, didn't perform so well on a site that had a resonant period. The site period and the structural period were in a similar range, and so you got amplification between the soil profile and the structural response.
A gross simplification of it might be, let's start putting flexible buildings on stiff ground and putting stiff buildings on flexible ground. So we just keep well away from this resonance spot. So we're going on to talk a bit more about soil structure interaction. The main thing we'll be talking about is the basics and what matters. So don't expect either Hamish or myself to be talking about 3D, time history and all other such complex things, because we both really agree that what's the important things is getting the simple things right. So let's talk more about that. So first of all, what is soil structure interaction? Well, here's what I'd suggest it is. It's first of all the load displacement behaviour of the soil, and then it's what is the response of the structure to that. And there's sort of two aspects to that. First is what are the deformations of the soil and what increases in actions is that actually causing in the structure. And the second thing is what is the shaking response of the building due to any flexibility that you may have in the ground, and how does that therefore the demand coming back onto the ground. So the first aspect of that I want to talk about was the building period, the seismic response of the building. So the first thing you probably would normally do is just look at a fixed base. But then in some cases, it'll be then worthwhile to go on and explore the possibility of what flexibility is in the ground, and does that actually modify this response of the structure. So we need to be careful here that we don't kid ourselves that the ground is more flexible than it really is. So we need to be using the stiffer end of that range of stiffnesses. In contrast, we need to be thinking about deformations and the differential settlement in the building. So there we need to be thinking about the other end of the range. How flexible could the ground be? How big could those differentials in the building be?
And I suppose, you know, just coming back to that one at the top, allowing a little bit of a softening of the building response because we've got a flexible soil, as Stuart said, you know, that's potentially reasonably dangerous territory, and we need to be pretty confident that we have got confidence that that's going to happen, and before we took advantage of that. And I'd suggest that sort of 99 times out of 100, if not more, we probably wouldn't be able to convince ourselves that. In fact, I'm not aware of any time in my career that we have. So that would be certainly the exception, not the rule.
And here's the exception. So thinking about a multi-story building on a big raft foundation. So what we probably really need to do here is think again about the two extremes, but we've got to think about how we go about it. So first of all, thinking about how stiff the ground could be. So that is, how big could the response be? How big could those demands be as a consequence? But in conjunction with that, we need to be careful that we don't then use the weakest ground conditions, because you're not going to have the stiffest response to the structure sitting on weak ground. So when you start thinking about the bearing capacity and whether or not you're getting yielding of the ground, if you've used stiff parameters, then you need to use strong soils. In contrast, you then need to think about the other extreme, and that is, oh, maybe the ground is a lot softer than I think, but then of course your demand's going to go right down. So you think about soft ground, reducing the demand, but in conjunction with that, you need to also think, okay, the bearing capacity of the ground could be less. So think about the two extremes, but don't cross it over. You know, stiff ground plus weak ground just doesn't make sense.
But at some stage, you probably are going to need to consider the stiff ground response on the structure, but not necessarily stiff and soft soil at the same time. And I suppose, you know, just thinking about how we'd approach a modelling exercise in terms of soil structure interaction. There was a couple of presentations at the recent SESOC conference that really brought this to light around, you know, making sure we keep things as simple as possible. And so the keep it simple, stupid principle certainly comes to mind. And certainly as a starting point, considering the least complex model that will provide the minimum level of accuracy that you need. So not trying to start with something that's more complex than it needs to be to get the level of accuracy in the answer that you're after. And there were a couple of really good presentations and or papers from John here as a keynote, and then a paper by Nick Brook and Tony Stuart around modelling that are worth a look if you've got access to the conference proceedings. And then, you know, sort of where do you start with a modelling approach to soil structural interaction? And the suggestion is to start simple and to iterate and know when to stop. And so knowing when the answer you're getting is as accurate as it needs to be and you don't need to go any further is really important philosophy in terms of, you know, what we're trying to get across tonight. So, you know, certainly starting with empirical methods like BROMs, if you're looking at lateral load on piled foundations, and with some, you know, good geotechnical parameters from your geotechnical engineer to use in conjunction with those empirical methods, that in many cases might be as far as you need to take things, and a BROM's answer to a problem might be sufficient. You know, from there, maybe you do need to take it a bit further because you've got different soil profiles, or a BROM's approach isn't valid. But you might start to think about simple single pile spring models. Again, getting some soil stiffness parameters from your geotechnical consultant, putting some load on your pile, and then, you know, working those through with your geotech consultant again. You know, that iteration, okay, we've got this spring, it led to this deflection, what does that do to your stiffness? And iterating through a single pile spring model. And again, in a large number of circumstances, that might be as far as you need to go. You might have a building that's got 50 piles, but if you know where the load is going and how much shear is being taken by what piles, assessing a worst pile in terms of a single spring stiffness model might be as far as you need to take it. And then from there, you could, if you wanted to, build more complex models, but you'd need to understand why you're wanting to do that and be very careful that the effort involved in doing more complex modelling is actually worth the benefit of doing it. And always looking to loop back to understand what it all means for the structure and with ongoing structural geotech feedback. And the last thing we want to suggest is very complex 3D structural and soil spring models all combined. And you can very quickly get yourself into the situation as you don't know what's driving what and whether the response is driven by the soil or is it driven by the structural solution, or and those sorts of very complex three-dimensional models become very hard to debug very quickly. Anything to add there, Stuart?
No, that was good, Hamish. That's good. So what I want to talk about here is that it's actually simple. What do we mean by a vertical spring stiffness? Maybe I'm stating the obvious, but all it is just load divided by settlement. And I think we lose track of that as geotechnical engineers. Like, all we really need to do is calculate a settlement and take the load divided by the settlement, and there we've got the spring stiffness. But a couple of things we just need to be a little bit careful of there, and that is, first of all, what is the load range we're interested in? So in the case of design of a new building, we'll have a strength reduction factor in there of 0.5. So it's only sort of the first half of the capacity of that foundation that we're really interested in. So it's going to be that initial stiffness and what is the range there. In contrast, if we're thinking about terms of a assessment of an existing building, we might be interested in what the load displacement of the foundation is right through its full capacity. In which case, then we've got to think about the non-linear behaviour that's going on and actually how we model that. And we'll talk a little bit about that in a moment. And the second point is the rate of loading. We need to be thinking about what is the purpose of this. If it's a seismic assessment, it's going to be short-term loading. So therefore, it's going to be short-term displacements, short-term spring stiffnesses. In contrast, if we're interested in the long-term static settlement situation and the soil structure interaction, again, it needs to be the long-term settlement predictions. Yeah, what are the stiffnesses? What are the units of stiffness? Are they meganewtons per cubic meter or kilopascals per millimeter? Anyone know the answer? They're actually exactly the same thing, aren't they? But the point I'm trying to make is, let's communicate. I have no idea what 300 meganewtons per meter cubed actually means, but 300 kilopascals per millimeter does mean something to me. If I've got a 1 meter by 1 meter pad foundation and I put 300 kilopascals on it, I'm going to get 1 millimeter settlement. So it actually means something, and it's, you know, I'm sure you're understanding what I'm talking about. So let's communicate. Let's actually think about what these numbers we're throwing around between each other actually mean. The next point I wanted to make is trying to come up with these load displacement behaviours of foundations is not really that complicated. And I'd just like to quickly talk through an example of a pile foundation and how you might come up with a load displacement behaviour. So here a plot, obviously vertical axis load, and then the horizontal axis settlement. So the stiffest part of that pile is going to be its shaft resistance, most likely, for a pile in soils. And we would expect to develop most of that shaft resistance, not all of it, within about 5 millimeters of movement. So we've immediately got 0.1 on the graph. That is the shaft resistance of the pile and 5 millimeters of settlement. The next thing that's probably going to come in stiffness terms is going to be the end bearing of the pile on the soils beneath it. So we can very simply do a bit of elastic analysis around how much that's going to displace with increasing load. Well, we've got point number 2. And then finally, point number 3. When we talk about the capacity of a pile, we're actually talking about a nominal capacity. That nominal capacity of around about 10% at a displacement of around about 10% of the pile diameter. So we've got 0.3, nominal capacity and 10% of the pile diameter. And then we can draw a curve through it. The next thing we need to be thinking about is, okay, we've got a load displacement plot there. Now, how between the geotechnical and structural engineer are we actually going to model this in the structural analysis? So that's a good time to actually share that curve with the structural engineer and talk about what parameters we're going to come up with. So as we talked about before, in design of a new building, we've got a strength reduction factor of 0.5. We're really only interested in the bottom half, and there'll be a fairly narrow range of spring stiffnesses we'll be interested in. In contrast, we're assessing an existing building, and we're looking at the full range potentially of that load displacement behaviour. We need to think about how we're going to model that. And the suggestion here is as a sort of an elastic plastic sort of model to be a very poor representation of that non-linear behaviour. Again, communication, we're all guilty of it. The left-hand side, what we put in our reports, what does that really tell us? Wouldn't it be a whole lot better to put in our reports what's on the right-hand side? It actually tells the full story, whereas what's on the left just gives us one little snippet somewhere along that curve that we've drawn. So just encouraging us to use pictures. This is one I hear just continually, halve it and double it. Why? Aren't we better to be thinking about how soft can this foundation be and how stiff can this foundation be? So first of all, think about what are the stiffest we would expect the soil conditions to be. Go through and calculate the subgrade modulus of your foundation, and then think about how soft those ground conditions can be and recalculate it. And now you've got a real range rather than, I don't know why, halve it and double it, but admittedly it often works. Okay, now we've got this range of stiffnesses, the softest we think it could be and the stiffest. What do we then do about it? What do we do with those numbers? So what the geotechnical engineer needs to think about is how does that vary across the site, and therefore how's that going to be modelled in the structure? So probably just describing this by a couple of examples. First one for either piles or pads sitting on an alluvial deposit where you've got these quite isolated silt lenses. So anywhere within the site you could end up with a softer spot. So how we would model that is by modelling, say, one or two of the foundation points, grid points, with soft springs, and the rest possibly rigid base, possibly stiff, and just see what that does to the structure. And you would position that spring, that soft spring, in the worst place, which is probably beneath the most heavily loaded pile. In contrast, the geotechnical engineer might be thinking, actually what happens because of these ground conditions is I'm going from soft on one side of my site through to stiff on the other. Well, let's model that. Let's talk to the structural engineer what sort of impact that variation in stiffness could have.
And for the structural engineer, I mean, often the issue isn't global settlement. The issue is often differential settlement. So it's not just how much differential we might have, it's how much differential we might have and how close that differential might be to another, another foundation element. Similarly, when we're designing a raft foundation, what the geotechnical engineer needs to think about is how does that stiffness beneath the raft foundation vary across the footprint of the raft. Could you expect a soft spot? How big could that soft spot be? So thinking a little bit about your geology and how the ground conditions could vary. So you might come up with, say, I think the soft spot's going to be 5 meters by 5 meters. So talk to the structural engineer about that and say, okay, we need to model this. Let's use some softer springs, 5 meters by 5 meters. Don't really know where beneath the raft that's going to be, so it better be in the most critical spot, probably under a corner or along one side, so we can model that. And sort of the overarching thing we're getting across here, hopefully, is just talk to each other. It's all really about effective communication. So look, the idea of being curious about each other's disciplines and seek to learn from each other and ask questions and be prepared to ask the dumb question or the question that you might think is the dumb question, but might actually be the thing that you should have asked all along, and it prompts a good conversation. I think something that I've certainly learned over the years is to kind of understand what the common language is and make sure you understand what each other's talking about. And if you don't understand what ultimate geotechnical capacity means, ask. and does it include a strength reduction factor or not, and all of those sorts of things. Make sure you're using a common language and are actually talking to each other about the same thing, because I think we often don't do that very well, and talk across each other at times.
Yep. Guilty at times.
And also understanding what's important, not only to each other, but to achieve the common goal and the design solution that we're ultimately looking to arrive at. And again, Stuart has talked about the idea of the feedback loop and talking to the structural engineer, talking to the geotechnical engineer about the fact that that spring value is really soft and it's had a impact or not on the structure, and often it might not. And so a geotechnical engineer can potentially run down a rabbit hole worrying about the accuracy of the spring stiffness they're about to give the structural engineer, when it actually doesn't really matter all that much. And the structural engineer, whether it's 10 or 15 or 5 doesn't make much difference.
Absolutely. Before we came in here, we were having a bit of a conversation around intimidating structural engineers, which I know from bitter experience, there's plenty of them in Wellington. So really encouraging in our organisations to actually get this collaboration and discussion going at all levels within our organisation. It's pretty blimmin' hard for a graduate engineer to go and talking to, whoops, I won't mention names, but some senior structural engineers in this city who can be fairly intimidating people. So just try and get in our organisations that communication happening at all levels, so we can start to understand each other's language and get that communication going throughout our careers.
And look, absolutely the best way to communicate is face to face, but don't be afraid to pick up the phone, and at absolute last resort, potentially send someone an email.